So we want to talk about infinite series. So the starting point is you start with the sequence of numbers and then you add all of them up. So you have A1 plus A2 plus A3 plus A4 plus dot 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 AN plus dot dot dot. If you keep on adding this, you get what is called an infinite series, and it's denoted by symbol summation n equals to 1 to infinity of an to denote where the n is ranging for, or just simply summation an. In that case, it's clear that it starts from n equals to 1 to infinity. However, infinite addition in mathematics doesn't really make sense directly. So what we'll do is we'll try to approach it in terms of limits. So the idea is you start with the summation n equals to 1 to infinity of ai as series. You define what is called as sequence of partial sums. So you start with S1, which is just adding first term, S2, which is just adding first and second term, S3, A1 plus A2 plus A3, or Sn is going to be A1 plus A2 plus A3 plus An. So this Sn is called nth partial sum. Okay, so this Sn is called nth partial term. Okay, so nth partial sum. So now how do you define this infinite series? So this infinite series can be defined now as I going from 1 to infinity of ai can be thought of as limit as n goes to infinity of this I going from 1 to n of ai, or it can be thought of as limit as n goes to infinity of Sn. So your infinite series now is basically limit of this sequence. All right. So now there are some interesting sequences which you can see. If you go on Wolfram alpha, you will see that summation n equals to 1 to infinity of 1 by n factorial is equal to e. Okay. Similarly, if you go and look at summation n equals to 1 to infinity of 1 by n square, this is pi square by 6. Okay. So these are some examples of there's another example basically, which is summation n equals to 0 to infinity of minus 1 to the power n upon 2n plus 1 is pi by 4. Okay, we'll make these connections at the end of couple of lectures. You'll be able to see why this is the case. All right. You'll also see that summation n equals to 1 to infinity of 1 by n basically does not goes to fixed number. In fact, it diverges to infinity. So with this kind of ideas in mind, let's move ahead. Okay. So given a series summation I going from 1 to n of ai, which is a1 plus a2 plus a3 dot dot dot, let Sn denote the nth partial sum. That means what? You add a1 plus a2 plus a3 plus a4 plus a5 all the way until an. And in short, this can be written as summation I going from 1 to n of ai. So now if this sequence converges, which we have idea about now from the previous lecture, that if this sequence converges, then we say, and if sequence converges to S, then we say that the series is also convergent, and we write summation I going from 1 to infinity of ai as a1 plus a2 dot 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 equals to S. So this number S is called sum of the series. Okay. So if the idea is if the sequence of partial sum converges, then the series converges. And to what does the sequence of partial sum converges is the sum of the series. If the sequence of partial sum does not exist, then we call the series to be divergent. Okay, so that's the idea. Now notice the following. If you take the series 1 plus 2 plus 3 plus, 1 plus half plus 1 by 4 plus 1 by 8 plus 1 by 6, so on and so forth, you will be able to see that S1 is 1, S2 is 1 plus half, which is 1.5. S3 is 1 plus half plus 1 by 4, which is 1.75. S4 is this. In general, it turns out that Sn is 2 minus half to the power 2n minus 1. So if you look at the limit as n goes to infinity of Sn, you will see that this is same as limit as n goes to infinity of 2 minus half to the power n minus 1. And as n goes to infinity, this guy goes to 0. So we have the limit is 2. So this series is convergent and it converges to 2. Okay. Now, so the question is, can we always find where does the series converges or what does it converge to? So the answer is not really. But for certain special series, we can find out what the sum is. So the first among those is what is called as geometric series. So what is a geometric series? So geometric series is basically you have A, you have AR, then you have basically AR square, AR cube, so on and so forth. So recall this was your geometric sequence, and you add the element of geometric sequence, you get a geometric series. You get geometric series. So now we want to basically compute when does it converges, and if it converges, to what does it converge? Okay, so we want to compute the nth partial sum, right? Now to compute the nth partial sum, let's look at Sn, which is going to be A plus AR plus AR square dot 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 nth term is ARn minus 1. So you can take A common, what is left in the bracket? 1 plus R square dot 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 R to the power n minus 1. Now recall, we had 1 minus R to the power n is going to be 1 minus R times 1 plus R square dot 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 R to the power n minus 1. Right? This is an expansion for this, right? So you can think about from here, you can see that 1 minus R to the n upon 1 minus R is equal to 1 plus R square until R to the power n minus 1. So instead of this guy now, instead of this, I can write it as A 1 minus R to the power n divided by 1 minus R. So this is my Sn. Now if I take limit as n goes to infinity on both sides, so limit as n goes to infinity of Sn is going to be limit as n goes to infinity of A 1 minus R to the power n divided by 1 minus R. Now, you know that this converges. So this converges, what? When does it converges? Converges if absolute value of R is less than 1, and diverges when what? Diverges when absolute value of R is greater than 1 or R equals to negative 1, right? And also for R equals to 1, this is not defined. So really this is basically limit as n goes to infinity of this is going to be A upon 1 minus R if absolute value of R is less than 1. Yeah. So what do we get? Therefore, we have that this series converges only when absolute value of R is less than 1. And not only that, it tells you where does it converges to. Yeah, it not only tells you that it converges, but it also tells you where does it converges. All right, so which is quite strong in statement in some sense. Let's look at the following ones. Now try to do these problems. So can you basically, if you look at this, A can be written as summation n equals to 1 to infinity e to the power 10 e divided by 10 times e to the power 10 power n minus 1. So we are writing it in a form so that we can read what is A and R. What is R? R is e by 10 and A is also e by 10. Now absolute value of R is same as e by 10, which is less than 1. Why? Because e is roughly 2.71 something. So we can see that we get absolute value of R is less than 1. So therefore, this series converges. So this series converges. And converges to what? Converges to A upon 1 minus R, which is E upon 10 upon 1 minus E by 10, which is going to be E over 10 minus E. Okay. Let's look at part B. So for B, we again combine it together. So summation n equals to this. I'll bring minus sign inside. So I have minus 3 by e to the power n, which can be rewritten as n equals to 1 to infinity minus 3 by e times minus 3 by e to the power n minus 1. Here r is minus 3 by e and absolute value of r is 3 by e, which is greater than 1, right? Why? Because 3 is greater than e, therefore 3 by e is greater than 1. So therefore what happens? This series diverges. Okay, so now let's look at another problem. Express 0.55555 as a rational number. So let me make this problem slightly more interesting. 0.75757575. And let's express this as a rational number. Okay. So how do we go about it? Well, one way is to write it as a geometric series. So let's see. So if you write it as geometric series, what do we get? This is same as 0.75 plus 0.0075 plus 0 followed by 4075 and so on. So if you notice, the first term is going to be 75 by 100. Second term is going to be 75 by 100 but multiplied by another 1 over 100 so that it moves 4 decimal places. Next one is going to be 75 by 100 multiplied by 1 by 100 square and so on and so forth. So this can be written as a geometric series with n equals to this 7500 times 1 by 100 to the power r minus 1. Although you can have directly seen that here, that A is 75 by 100, R is 1 by 100, and since absolute value of R is 1 over 100 is less than 1, the above series or the rational number, because they are the same thing, right? We wrote the rational number as a series, converges to 75 A upon 1 minus R, which is 75 by 100 divided by 1 upon 1 by 100, which is going to be 75 by 100 divided by 99 over 100, which is 75 over 99. So this is what it converges to. Does that make sense? Okay. So this is about the geometric series. Now let's look at the following series. So show that the series which is given by the following, converges, and find where does it converges to. Okay. So now let's look at Sk. So first let's look at Sk is going to be summation n equals to 1 to k of 1 upon. Now you can use the partial fractions to see that this is going to be 1 upon this upon n plus 2. So when you write this down, you will see, and when n is 1, what do you get? You get 1 by 2 minus 1 by 3. When n is 2, what do you get? 1 by 3 minus 1 by 4. When n is 3, what do you get? 1 by 4 minus 1 by 5. And you keep on doing this until you get 1 by k plus 1 minus 1 by k plus 2. Now note that these guys cancel out. This 1 minus 1 by 4 will cancel with this. So all of the internal guy gets cancelled and you're left with this is equal to half minus 1 upon k plus 2. So limit as n goes to, k goes to infinity of sk is limit as k goes to infinity of half minus 1 upon k by 2. And as k goes to infinity, this guy goes to 0, right? So we have this is equal to half. So therefore, summation n equals to 1 to infinity of 1 upon n plus 1 times n plus 2 equals to half. So such a series is called telescoping series. Okay. So for example, if you look at this series, it's going to be slightly involving to show that that this series is equal to pi squared by 6, right? Or for that matter, it would be hard to find out where does this series converges to. So if this series is convergent, we'll see later. So the idea is sometimes we are just happy with the fact, knowing the fact that the series converges or diverges. Okay. So in that sense, we have the following result. So we know one series, which is the harmonic series, and that diverges. So this is very important. So let's pay attention to this. So how does my S1 looks like? So S2 is 1 plus half, right? Which is going to be what? 1 plus half. So what about S4? So I'm basically jumping through it. I'm not writing S3, but I'm going to write S4, then I'm going to write S8, and you will see that why. So S4 is going to be 1 plus half plus 1 by 3 plus 1 by 4. Now I can combine these two together, right? I can combine them together. So each one is, so this is going to be greater than 1 plus 1 by 2. And of course, 1 by 3 is greater than 1 by 4, right? So I can write this as greater than 1 by 4 plus 1 by 4. And that can be written as what? 1 plus 1 by 2. This is going to be another 1 by 2, which is going to be 1 plus 2 by 2. Let's look at S8. Is going to be 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8. So again, in this case, we'll combine these two guys and then we'll combine these four guys. And how am I combining? So this is going to be 1 plus, we have already seen that is half. We have already seen that this can be written as greater than, this can be already written. So S4, so this part can already be written as greater than 1 upon 2 plus 2. And then for the other part, we'll have that is also bigger than 1 by 2, right? Because you can replace this by 1 by 4, replace this by sorry, 1 by, you can replace this by 1 by 8. So 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8. And that is going to be 1 plus 2 by 2 plus 4 by 8, which is going to be 1 plus, if you look at this correctly, carefully, it's 1 plus 3 by 2. So if you keep on continuing this, you will see that S of 2n is greater than 1 plus n by 2. Okay? Because what is S8 is 2 to the power 3. Yeah. So you see that Sn is greater than this. So therefore, limit as n goes to infinity of S of 2n is going to be greater than equal to limit as n goes to infinity of what? Of 1 plus n by 2, which is going to be what? Infinity, right? So we get that what? This series, so the sequence of partial sum diverges, we see that the whole thing diverges. Okay, therefore Sn diverges, which implies summation 1 by n diverges, because after all, the convergence of divergence of your series is same as convergence and divergence of your sequence of partial sums. So if P implies Q, then we have negative Q implies negative P. Okay. That means if the series an converges, then limit as n goes to infinity of an must be 0. Why is that? Let's see why is that the case. So we have Sn plus 1 minus Sn. This is going to be a1 plus a2 dot 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 an plus 1 minus a1 all the way until an. So let's just take a Sn minus 1. So this is going to be an minus 1. So this is going to be an. Now suppose if your sequence is convergent, sorry, if the series is convergent, this means what? Limit as n goes to infinity of Sn minus 1 is limit as n goes to infinity of an. Now as n goes to infinity, if the sequence is convergence, it will converge to same number, say s. S minus s equals to limit as n goes to infinity of an, which is what? Which implies limit as n goes to infinity of an is 0. So you have shown that limit as n, if Sn converges, or if the series converges, then the n term must go to 0. Now, what is the contrapositive of this statement? If limit as n goes to infinity of an is not 0, that means it's not 0 or it does not exist, then the series diverges. So this test is called divergence test. Okay, so this is called test for divergence or test for divergence or divergence test. Okay, whatever you call divergence test. So what is the test for divergence? It is basically seeing that if your series is divergent right away. All right. So if limit as n goes to infinity of an is not 0 or does not exist, then you right away get the divergence. But note that converse is not true. For example, you see this series here, limit as n goes to infinity of an is 0, but the series is divergent. Right? So it's not that the limit an equals to 0 means the series is convergent. All it means is the following, that if it is not 0, then it's going to diverge for sure. Okay. If it goes to 0, then you don't know. You have to apply some other test to see. So now let's see. Show that this is divergent. So here your an is n sine 1 over n. Now, what is limit as n goes to infinity of an? We have limit as n goes to infinity of sine of 1 over n divided by n. So you can write this as divided by 1 over n. And this limit is what? 1, which is not 0. Therefore, what? Summation n equals to 1 to infinity n sine 1 over n diverges. So in some sense, divergence test is the first test to basically see about series whether it converges or diverges. Now we'll look at many tests throughout for a couple of lectures on tests to see whether the series converges or diverges. Okay. So these are a few properties of convergent series. Note that this is only true for convergent series, all right? So you have two series, an, summation an and summation bn, and they both are convergent. Let C be a constant. Then summation CAN, summation AN plus BN, summation AN minus BN is also convergent. And not only that, what is the limit of these series? So let's see that. So sub C times summation AN, the constant can come out. So you get C summation AN. For summation AN plus BN is same as summation AN plus summation BN. If you replace this by minus sign, then this will be replaced by minus sign. Okay. So let's do the following problem now. So we want to find out if n equals to 1 to infinity of 5 by 2 to the n minus 2 by n plus 1 times n plus 2. So if this series is convergent, find its sum. So you have already seen this example in 6, summation 1 by 2 to the n converges and summation 1 upon n plus 1 times n plus 2 are also convergent with somewhat. So the first one, the sum is actually 1, not 2. Okay, so this sum is 1. All right, why? Because you're starting from n equals to 1 to infinity of 1 by 2 to the power n. Let's work it out. So here your a is 1 by 2, r is also 1 by 2. So we get what? Since the absolute value of r is less than 1, this converges and it's going to be a divided by 1 minus r, which is half divided by half, which is 1. So in this case, what I can do is I can take 5 out and write summation n equals to 1 to infinity of 1 by 2 to the n minus 26 times summation n equals to 1 to infinity of 1 by n plus 1 times n plus 2. This is going to be 1, so this is 1. And so we have 5 times 1 minus 26 times, this we already computed to be 1/2 right here. So if we go back, we found out that this series converges to half. So we get this is equal to, so you put half here. So this is going to be 5 minus 13, which is going to be 5 minus 13 is minus 8. So this is what your series converges to.